to you guys, and it's going to be, please talk to them after, get to know them. The second thing I need to do is to introduce the events in the coming days. On Friday, we have the second lunchtime talk given by my colleague at the Department of History and Philosophy of Science, Nina Atanasanova, who is going to be talking about the surreality of pen. The talk will be on Friday at noon, from noon to 1:30. There is no talk on Tuesday next week. We had to cancel Wen Myhrvold's talk for reasons that don't really matter. So there won't be any talk on Tuesday. So the next talk, the talk next week will be given on Friday by our new colleague at CMU, Aidin Mohseni, who just joined the philosophy department at CMU, a former postdoc here at the center, and who will be talking a bit about a Bayesian reduction of causation in causal models. So come and listen to Aidin's talk. The last thing I wanted to, the two last things I wanted to mention is the first conference of the semester that will be taking place from the 25th to the 26th of October. It's a conference in the philosophy of neuroscience, a population doctrine in neuroscience, organized by my colleague Wen Wu. You can register for the conference online on the center's website. If you plan to come, I ask you to do that, so that we have a head count. And the program is also now online. So if you want to know who is speaking, just go to the center's website. And the last thing, the last announcement is a call for papers for a conference that Jim Woodward right here is organizing. The conference is called "To Be or Not to Be Included in a Causal Model." So we have a call for paper for this conference on causal modeling and on the nature of causal variables. The call for paper is also on the center's website. So please have a look and submit a proposal if you're interested. Today, it's my pleasure to introduce another of my colleagues, David Wallace, who is a Mellon professor in history and philosophy of science. He has a joint appointment in the Department of Philosophy and in the Department of History and Philosophy of Science. He's an extremely well-known philosopher of physics, and he really needs no introduction. He has been with us at Pitt for a few years before he was in Los Angeles at USC. And before that, he spent a lot of time at Oxford. He has a PhD in physics and in philosophy. He is the author of two books in the philosophy of physics, The Many Worlds Interpretation, a very well-known book about the Everett interpretation, which was published in 2012 with OUP, and a shorter book, Philosophy of Physics, a short introduction, also published with OUP in 2021. He has published many articles in the best journal, including this one, coming out in the next 25 years in the Journal of Philosophy. It's accepted. One day it will be online and one day it will be in print, maybe, if we still have print journals by then. But anyway, so that paper was accepted recently in the Journal of Philosophy. He's also, as you might know, the editor of the Philosophy of Physics, recently created, maybe 2-3 years or something like that. 3 years journal for the Philosophy of Physics. He is also the chair of the Department of History of Philosophy of Science. And sometimes I guess he sleeps. But today, David will be talking about local quantum vacuum as a past hypothesis.
Thank you. So in hindsight, it should perhaps have occurred to me that agreeing to give a lunchtime talk a week after starting as HPS chair might have some downsides. So I apologize in advance if some of this is a little bit chaotic. Okay, there is a hip. Yeah. It needs to select, doesn't it?
Here we go.
Yes. Okay, there is a well-known class of problems in the foundations of thermal physics and thermodynamics and statistical mechanics, which you might collectively call the irreversibility problem. And that problem essentially says, one, microscopic physics is reversible. It doesn't care about the difference between the past and the future. Or to be slightly more pedantic, it doesn't care about the difference between the past and the future in any way that seems relevant to the macroscopic. Mesoscopic physics, physics of systems with large numbers of degrees of freedom, is irreversible. Its dynamics makes a qualitative distinction between past and future. The equations of fluid dynamics involve viscosity and dissipation, and at the more human level, processes like the passing of youth, the decay of food, phenomena of this kind clearly display a direction of time that appears absent at the microscopic level. And so as a matter of logic, something has to break the microscopic asymmetry. And there are a whole bunch of proposals of this kind, some of which are coherent, some of which are not. People have looked at trying to modify the microphysics in response to this. People have supposed that somehow there are causal or agentic or epistemic effects that are even prior to the physics effects. But in the last 20 or 30 years of writing in the philosophy of statistical mechanics, the dominant set of ideas have involved one or other posit of some kind of boundary condition in the early universe, which has the characteristics to break the symmetry, a past hypothesis. That term comes from the philosopher David Albert. Albert didn't invent these ideas originally. They go back at least to Boltzmann, but Albert, to the best of my knowledge, certainly popularized the term past hypothesis. And a very large fraction of the discussion in the philosophy of physics literature has taken something like Albert's past hypothesis as a starting point for thinking about how fundamentally these symmetry and asymmetry are to be reconciled. And without prejudice to more foundational concerns you might have about that framework, I'm going to work in that tradition for this talk. I want to explore some aspects of Albert's proposal, or the past hypothesis as Albert precisifies it, in the context of contemporary cosmology. So, although he doesn't use this term in the original Time and Chance, in later work, Albert, working with Barry Loewer, came to call the framework he was discussing the Mentaculus. To understand why, I think you need to be much more immersed in New York Jewish culture than I am. So I'll just take that as a baseline primitive. Here's a statement of the Mentaculus, or of the view he came to call the Mentaculus, from Time and Chance. Quote, "The Newtonian statistical mechanical contraption for making inferences about the world consists in entirety of 3 laws and 1 contingent empirical fact. The empirical fact is the one about what the macro condition of the world currently happens to be, e.g. David is giving a lunchtime talk at 12 o'clock, and the laws are, 1, the Newtonian law of motion." Now he says, which is that F equals ma, but in context, I take that to be a placeholder for a sort of richer and more dynamically interesting Newtonian physics. 2, the past hypothesis, which is that the world first came into being in whatever particular low entropy, highly condensed Big Bang sort of macro condition it is that the normal inferential procedures of cosmology will eventually present to us. And 3, the statistical postulate, which is that the right probability distribution to use for making inferences about the past and the future is the one that's uniform on the standard measure over those regions of phase space that are compatible with whatever other information we happen to have. A great deal of real and virtual ink has been spilled on the conceptual structure of this set of arguments. What's the nature of these probabilities? What is the form of explanation in play here? To what extent is it problematic that anything cosmological should be tied to more parochial things like the viscosity of fluids in the here and now? There's lots to say on that. I've said various things elsewhere, but my focus here is going to be something on which rather less has been said, which is, if the past hypothesis is that the world first came into being in whatever particular low entropy, highly condensed Big Bang sort of macro condition it is, that the normal inferential procedures of cosmology will eventually present to us, which one is that? Presumably the normal inferential procedures of cosmology are ongoing. We don't have a final cosmology, so we presumably don't have a final answer to what this is. But cosmology's been kind of successful, kind of learned some stuff. We might think that we know enough about cosmology to say something more specifically about what sort of posit about the past, the initial macro state of the universe Albert's trying to make. And that's basically what I want to do in the talk today. I want to take a bit of time to just spell out a bit more of the details of Albert's framework, just as a kind of grounding position so we know where we're starting. And then I'm going to discuss a bunch of cosmological models and show how we might make sense of Albert's proposal, or the general shape of Albert's proposal in that context. As a spoiler alert, I think the very broad basic shape of Albert's framework survives fine in modern cosmology, and indeed fits in it with a reasonably natural way. but a lot of the details, including some of the details on which people have got quite philosophically fixated, change in interesting fashions. Okay, so let me, just to sort of ground this, particularly for those who don't work so much in philosophy of stat mech, but also to kind of put a placeholder down for those who do work in philosophy of stat mech on how I want to read some things. Let me just cash out Albert's past hypothesis in a bit more detail. It's helpful, I think, to break it into two past hypotheses, which you might call PHM, which is an assumption about the initial macrostate, and PH_mu, which is an assumption about the initial microstate. As everyone knows, the way statistical mechanics works is that we spend a lot of time talking about macrostates, macroconditions, macrodynamics, and a lot of time talking about microstates, microconditions, microdynamics. And it's extremely easy to mishear between those and get completely the wrong end of the stick. When I was taught statistical mechanics as an undergraduate, the teacher was an otherwise brilliant physicist with a sufficiently thick Russian accent that it was completely impossible to distinguish these words. I'm mostly going to try to refer to PHM and PH_mu to make it a little easier to distinguish that. But the idea is that PHM says what the initial macrostate was. And again, the initial macrostate is the one that's supposed to be given to us by the normal inferential procedures of cosmology. And PH_mu tells you what the initial microstate is given the initial macrostate. So PHM says this is the initial macrostate. PH_mu doesn't say this is the initial microstate. It says put a probability distribution over the initial macrostate, uniform with respect to the standard Liouville measure of classical mechanics, and that distribution, whose foundational status is opaque, should be used to select the initial. I should say that Albert doesn't originally make exactly this distinction in Time and Chance. He states the probability distribution as a probability over the present microstates, but you can rephrase it losslessly in this way, and I think in more recent work Albert thinks that's somewhat clearer as a way of saying it. So here are a few notes about the past hypothesis in Albert's setup. So the first is, it's really crucial that PHM is a placeholder for a hypothesis about a specific macrostate. It's often misdescribed in the thermal physics literature as being the hypothesis that the initial state of the universe has low entropy. It's not that at all. It doesn't say anything about entropy. It says it's a placeholder for saying that there will be a state delivered to us by the inferential procedure of cosmology. That's what the past hypothesis, that what PHM says. That state will be presumably a high density, highly condensed Big Bang sort of state. And by the way, it will probably have low entropy. But entropy is not being used in the machinery of Albert's past hypothesis. Okay. Secondly, that means it doesn't rely on entropy, which is arguably a kind of inherently approximate macroscopic concept. It is nonetheless, as Albert sets it up, a little inherently high level and macroscopic because it uses this term macrostate. What are macrostates? Well, sometimes they're cashed out in kind of crudely operational terms, states that humans can distinguish or something. More reasonable for these purposes and more natural in Albert's setup is that the macrostates are kind of the ones with respect to which macrodynamics can be written down. So for instance, what makes the macrostates of a fluid the right macrostates is something like you can write down autonomous dynamical equations for how those macrostates evolve, things like the Navier-Stokes equations that abstract over the micro details. So that means that the notion of macrostate is although it's part of a fundamental law in some sense, is nonetheless reaching out to higher level emergent law-like concepts. That's not necessarily a vicious circularity, but there's a certain kind of interesting tension there. Third observation, there's effectively a division of labor here. The thing that's doing the work is the conjunction of PHM and PH_mu. Between them, they say something like, the initial microstate of the universe is selected by a random probability distribution over such and such region delivered to us by cosmology. The break it into the two parts is expositionary, but actually it's only that joint statement on the probability distributions over microstates that's doing the work. Fourth observation to Albert, those probabilities in PH_mu are classical probabilities. What those mean is complicated and mostly beyond the scope of this talk. But to Albert, there's something like for those who are more metaphysically inclined, Humean best system chances. They're something like the best description of the world that you could give would be one that abstracted away to probabilities rather than trying to tell you all the fine details. And these probabilities are the things that be in the description. I mean, Albert has a nice metaphor that's perhaps worth briefly mentioning. He imagines he goes to see God and he says to God, tell me about the universe. God says, well, there's a particle that at this time is at this position, and there's another particle that at that time is at that position. There's another particle at that time that's that position. And about that point, sort of, Albert stops God and says, look, this is sort of all very interesting, but I've got other things to do today. I've got to learn about the universe. So can you give me something a bit more succinct, something I could fit on the T-shirt? And okay, God thinks for a moment, probably quite a short moment, God being God, and then writes down a set of probabilistically stated laws, which are the best kind of intermediate choice between strength and simplicity. I'm not ultimately going to defend this account of laws. I think ultimately it's not probably viable, and in any case, a little overtaken by events and development of physics. But just again, to understand where this project is coming from, that's how the probabilistic laws are to be understood. And now we come on to where I'm going with this talk. There's a tension between Albert's reference to Newtonian physics in part of the past hypothesis and his appeal to modern cosmology in other parts of it. So go back to the Mentaculus. Step one is the Newtonian law of motion. And step two is something given to us by the normal inferential procedures of cosmology. And I think one thing we can be reasonably confident of, even though cosmology is an incomplete science at present, is that the normal inferential procedures of cosmology are not going to give us a piece of Newtonian physics. The normal inferential procedures of cosmology are not going to give some piece of physics that's stated in terms of non-relativistic, non-classical laws of motion for point particles or even classical fluids or so. So that's the starting point to ask, what does all this look like if we look at some of what we actually know about cosmology and apply it to as well as we can to this setup? So I'm actually going to consider sequentially three cosmologies. The first is a fiction. It's a genuine Newtonian cosmology, as various people in this room, not least John, have pointed out to us. There are deep problems in building Newtonian cosmologies, but you can build models that have enough enough cohesion that you can ask some questions about them. Nonetheless, that model is a fiction. I'm then going to discuss, as the second choice, classical Big Bang cosmology, which is not a fiction, but was an approximation, a higher level emergent description. Roughly adequate to describe our universe from 380,000 years after the Big Bang through to stellar formation. And then I'm going to discuss inflationary quantum cosmology, which is also almost certainly not a fundamental theory, but is the current state of the art in cosmology. I'm going to finesse a lot of technical details here. Many of them are over my pay grade, and in any case, I don't want to get bogged down, but I'm happy to go into more of those details in the Q&A insofar as they don't go over my head. Okay, so here's the Newtonian setup I want to have in mind. I'm imagining flat space, vast but finite number of identical, equal mass m point particles. They're all interacting under this two-body potential. So the first term there is the well-known Newtonian inverse square law of gravitation, inverse square forces, so inverse linear potential, plus some placeholder short distance repulsive force that regularizes this. And basically think of these as hard spheres that bounce off each other if they get too close, but where that repulsive force goes to zero very quickly if the particles are then just governed by Newtonian gravity. And to avoid certain cosmological problems, the particles are in a box. It's finitely but extremely large. So we can ask, okay, in this fictional setup, how might something like Albert's framework play out? And here's, given this as a fiction, this is just this is sort of stipulative for illustration rather than this is the correct choice, of course. This theory is false, it's not even approximately true. So there's no idea that these are correct or incorrect. These are illustrative versions that give an interest in cosmology. So here's my setup. PHM says the initial macrostate is a spatially uniform distribution of particles overall at rest. PH mu is the probability distribution over microstates compatible with the initial macrostate is uniform in the Loewer measure of phase space, so the usual pH mu. And then we ask, given that setup and given Newtonian dynamics with the potential I've just written down, what happens? How does that universe evolve at the micro and macro level? Well, the critical question is what the sign of G is. I told you that was Newtonian gravity, but I didn't tell you what G is. It's just a real number. If G is 0, of course, this system is boring. If G is less than 0, then this is a repulsive force. And in that case, the system will basically stay as it is. There might, by sheer chance, there might be slight fluctuations where there's a slightly higher particle density here than here. But if there is, because the force is repulsive, it'll flatten out again. So this system is basically the classical dilute gas in a box. It's at equilibrium in thermal sense. It stays there for eternity. Small fluctuations happen within equilibrium or around equilibrium. They're damped back down. If G is interesting, sorry, if G is, Freudian slip there. If G is greater than 0, so the force is attractive, everything becomes completely different. Now, if I have small fluctuations, they don't damp away, they magnify exponentially. It's called Jean's instability in structure formation in galactic dynamics and cosmology. So what the system will do is increasingly display a form of clumping, structure formation. And if we had a more interesting theory, then things might clump enough that things like stars might start forming. In this theory, they'll sort of clump together and stay together. But this universe is going to evolve increasingly in a highly inhomogeneous anisotropic way. Develop some of the details of that. First observation, this dynamics, the macro dynamics of this cosmology is going to be highly stochastic, which is to say, there aren't going to be deterministic laws that say how that uniform fluid macro uniform fluid is going to evolve that are just statable in terms of the macro condition. I mean, obviously there can't. The dynamics is isotropic and homogeneous. My initial macro state is isotropic and homogeneous. Nothing's there to break the symmetry, so there's no way deterministic dynamics can take the system to a scattered clump setup. But the dynamics isn't deterministics. Those small fluctuations invisible inside the macro state will magnify into larger fluctuations. And what that means actually is there's something slightly problematic about stating the cosmology in this way. If macrostates are supposed to be the kind of thing that we can use to write down macrodynamics, then actually this macrostate doesn't really do it for us because it's sensitively dependent to exactly how large the macrostate is. The bigger the region in phase space for the macrostate, the more fluctuations are compatible with the macrostate. So the larger part of the probability measure will be on relatively large fluctuations, and the faster the exponential growth of structure formation will be. So it really matters, unlike say in a ordinary repulsive fluid where the exact size of macrostates is kind of largely conventional and you get a robust dynamics where I just say I'll choose my macrostates to be large enough to contain a large number of particles, small enough to be small compared to the overall size of the system. Here it's extremely sensitively dependent. But there's a fix for that, and a fix that's very naturally in the spirit of Albert's framework. We can replace the separate pHm and pHmu with a single probability distribution over microstates, and it will be something like each particle is independently located at random in space and has some velocity distribution that you would be a new fundamental law what form it takes. You could, for instance, put in a Maxwellian probability distribution over velocities. A law of that form will be exactly the thing you need to write down the evolving cosmological structure formation. It will also imply, for any given sort of precisification of pHm, it will imply pHm with extremely high probability. So it will imply with extremely high probability that the initial state of the universe, the initial macro state of the universe is uniform as written. So the suggestion is that if one tries to take Albert's framework and apply it to this fictitious Newtonian cosmology, which is, I think, about as close as I can get to what's implied in Albert's background Newtonian physics, then you can get something that looks naturally a lot like Albert's framework, but which elides the distinction between pHm and pHmu. I should say also, sorry, with extremely high probability, this entails pHm, but it also clearly entails pH mu with respect to whatever the macro state is. Okay, so much for fiction. Think of that as that's a warm-up. That's kind of if God just decided that she was so impressed by Albert that she wanted to build a new universe exactly on the lines of his setup, this is, I think, presumptuous to tell God what to do, but I think this is probably what she should do. God's halfway through the second response, and David says, "No, I don't think you want to do it like this. This is the way you should be doing it." Okay, let's talk about some real cosmology. So I want to talk about and I'm going to talk in very general terms, the class of cosmologies that get called Freeman and Lemaitre, Robertson-Walken cosmologies. They describe the universe filled with and again, this is a macroscopic scale model. They describe the universe filled with a homogeneous isotropic fluid. That fluid's actual microdynamics is quantum mechanical. So we're inevitably at the level of a sort of high-level phenomenological description. But in any case, simply as a posit at the classical level, around 380,000 years after the Big Bang, that fluid becomes transparent, reaches the temperature below which hydrogen atoms form in effect. And at that point, radiation can pass through it. And then from that point, if you just take that as a starting point, cosmology is essentially classical from that point. There's no, to the best of my knowledge, no very interesting quantum mechanical phenomena we need to consider from the point to which we have transparency through to the point to which stellar formation starts happening and nuclear physics starts matching again. So we can approximate a reasonable chunk of cosmology in this kind of setup. And that's what I want to do for the next part of the talk. So here's what happens in classical Big Bang cosmology. As in the Newtonian model, we get structure formation. And we get structure formation for essentially the same reason. Initial small fluctuations in a largely uniform distribution feed on themselves, grow exponentially. And where you have a fluid that at 380,000 years after the Big Bang is very close to isotropic and homogeneous, a few gigayears later, you get something that looks more like that, which is a sky image of a big chunk of the actually what the universe looks like. You have this very complicated, somewhat fractal structure of strand. These things are like superclusters of galaxies. This is a little billion light year scale. Don't expect to be able to see Earth on this diagram. I mean, you can't anyway, it's taken from Earth, but even without that. So that looks quite a lot like the Newtonian story, but there's a very important difference. In the Newtonian story, remember, we started with a macro state that at the macro level was completely uniform. And structure formation in the Newtonian case, therefore, had to happen from the magnifying up to macroscopic scale of microscopic fluctuations in the matter distribution. That's not what happens in our classical cosmology model. Firstly, if the fluctuations in the early universe were only microscopic in scale, they actually just wouldn't be big enough to lead to the amount of galaxy formation we subsequently find. But more importantly, we know they're not microscopic in scale because we can see them. So remember, the universe becomes transparent at 380,000 years. That means the light that's sort of bouncing off ions at that point starts escaping. It keeps traveling. It redshifts over billions of years, and it arrives at Earth-based telescopes, or place-based telescopes in this case, in the present epoch. And that is literally a picture of what the universe looked like 380,000 years after the Big Bang. That's a picture. It's a heat map, but it translates to a density map. That's the whole universe, which was a lot smaller 380,000 years after the Big Bang than it is now, the whole of our causal patch, I should say. But these fluctuations are still kind of hundreds of thousands of light years across. So it's slightly vague, quite what we think the word macroscopic should mean, but on reasonable specifications, we've got macroscopic, primordial, from the point of view of classical cosmology, macroscopic fluctuations in the distribution. So that means that stating pHm in this model is a bit trickier. We can't say there is a particular macro state in which the universe, or this period of the universe, starts. That's the initial macro state relative to this bit of cosmology. It's clearly pretty complicated and messy. if you analyze it by taking moments and looking at their statistics, you find it has a very clean, well, mediated through various bits of physics we understand, it has a very clean mathematical form that can be described as a probability distribution over the night sky for the fluctuation. But that means the thing that the normal inferential processes of cosmology have delivered to us in this case is not an initial macrostate, it's a probability distribution over initial macrostates. So the nearest we could get to PHM in this classical model is something like this. The initial macrostate is an almost uniform thermal state, selected at random from a certain probability distribution over almost uniform states. But again, with that certain probability distribution being a placeholder for the actual distribution which the normal inferential processes of cosmology have in fact delivered to us. And then PH mu has its normal form. Once you've selected a macrostate for the beginning of the, or the effective beginning of the universe, the 380,000 year period, using this probability distribution, you then use another probability distribution, the Loewer distribution, to select the microstate with respect to that macrostate. So we've kind of, you know, if my Newtonian cosmology model wasn't just a fiction I made up for convenience, but was really something that was itself evidence, this would be a Kuhn loss. We were led to put together the PHM and PH mu into a single hypothesis. We've now pulled them apart again and gone back to something closer to Albert's original setup. Obviously, since I just pulled the Newtonian model out of the air, it doesn't actually have that philosophy of science implication. But there's something quite strange about this setup where I've got these two separate probability distributions in play. There's an awkwardness about a setup where I need to specify the initial macrostate probabilistically, and then I need to go in and put some more probability in and specify the initial microstate. Again, I kind of feel if God's explaining this to David, then he's really getting annoyed at this stage. You can't build the universe this way. So it would be interesting to ask more how we should think about these probabilities. And again, if this theory was something we imagine was exactly true, then there'd be some deep metaphysical questions to ask. But the reason for studying approximately true physical theories isn't to ask what would a fictitious world be like in which they're exactly true. It's to ask what do we learn about the actual world from thinking about these approximately true theories. And since all this is boundary condition data, we probably have to push further. And that takes us towards thinking about quantum mechanical versions of cosmology. And that's the last example I'll talk about. So to talk about that, I need to pause a little bit to talk about statistical mechanics and its foundations in a quantum context more generally. So the way Albert sets up his discussion in Time and Chance and the way in which the vast majority of foundational work in statistical mechanics has been done traditionally, although this is changing a bit, it all assumes classical mechanics is true. But of course, classical mechanics is not true. An adequate statistical mechanics needs to be quantum mechanical. And certainly a statistical mechanics adequate to probing the universe early in the transparency epoch certainly needs to be quantum mechanical. Right, so what would a quantum statistical mechanics look like? So the normal way we're thinking about a classical statistical mechanics is something like the system has microstates. It has a microdynamics that tells you how the microstates evolve. I can chunk the microstates into macrostates. If I choose my chunking correctly and I put in appropriate auxiliary hypotheses, I'll get out some kind of dynamics, maybe stochastic, maybe not, for those chunked macrostates. Superficially, you can do that quantum mechanically as well. In classical mechanics, the macrostates are subsets of phase space, and the microstates are the points of phase space. So natural thought is in quantum mechanics, the microstates are the points of Hilbert space, the vector space of quantum states, and the macrostates are the subspaces of Hilbert space, the closed, the linear closed sets of Hilbert space, or a certain class of them. So you can formally say something like, a macrostate partition in quantum mechanics is just a choice of a family of mutually commuting projectors on that space, summing to unity. The details of this are not going to matter too much for the talk. That looks great superficially. Push on it a bit and it comes apart. And this is fairly recognized. The root of the trouble is that while in classical mechanics, every microstate lies within a unique macrostate. That is not true quantum mechanically. So classically, if my macrostates were something like, I don't know, my cat is alive and my cat is dead, to pick a famous example, then if the cat were classical, well, it would then definitely dead, but putting that aside for the moment, if the cat were classical, then any given configuration is either a configuration of the live cat, or it's a configuration of the dead cat, or it's a configuration of that matter in some other state that isn't a cat of any kind. Quantum mechanically, of course, I have a linearity rule. So if there's a quantum microstate, which is the microstate of a cat that's dead, and there's a quantum microstate that's a microstate of a cat that's alive, there's a whole family of quantum macrostates, alpha live cat plus beta live cat, dead cat, that don't correspond either to the live cat or to the dead cat. That is, microscopic states can be in macroscopic superpositions. And this is, of course, the foundation of the quantum measurement. And a corollary of that is that it's not just that there exist in the abstract sense states that are macroscopically indefinite. It's that a state that's macroscopically definite can perfectly straightforwardly get into a macroscopically indefinite state. So for instance, in the famous Schrödinger cat experiment, Schrödinger's cat starts off macroscopically definite, it's definitely alive. And through the playing out of the experiment, it ends up in a, according to the underlying dynamics of quantum mechanics, it ends up in a macroscopic superposition of being alive. So we can't restrict our attention to the macroscopically definite state and hope to stay there. And that's an example where we explicitly built a machine to magnify the quantum indefiniteness to the macroscopic level. But in fact, the processes of statistical mechanical systems tend to do that routinely all the time. If I think about, for instance, the famous example of the pollen grain moving under the bombardment of water molecules that Einstein discussed in 1905. If you look for a quantum mechanical model of that theory, if you started off with a pollen grain that's determinately in one location, it'll fairly rapidly evolve until a superposition of pollen grains all over the place. Generally speaking, any kind of chaotic or mixing process, well, any process that's kind of chaotic or mixing classically ends up going over to a quantum mechanical process that tends to produce superpositions. Of course, we don't see macroscopic superpositions. And of course, that's the quantum measurement problem. And there are different ways of resolving the quantum measurement problem. Inside the sort of broadly realist observer-independent tradition, which can be challenged, but which I won't particularly challenge for the purposes of this talk, then the main range of options are things like either introduce some hidden variables that tell you what the real macrostate is, and suppose that a probability distribution over those hidden variables means that really the cat's alive or dead, even though the quantum state is a superposition of alive and dead. Or change the equations of quantum mechanics so that when you try to magnify a superposition up from the micro level to the macro level, something breaks, the Schrödinger equation stops working, some new random process kicks in, and the system stochastically jumps into either the live cat or the dead cat state. Or follow the Everettian approach, also known as the correct approach, and recognize that even if the universe as a whole involves the creation of macroscopically definite superpositions, macroscopically indefinite superpositions, then at the emergent and certainly at the observer relative level, things will appear as if there's definiteness because observers themselves will be branched by the process of interacting with the macroscopically indefinite system. The point is that a solution to the quantum measurement problem is effectively going to imply anytime we do quantum statistical mechanics of systems that are going to have these kind of chaotic mixing procedures. And of course, we've seen that the processes that lead to structure formation in the early universe have exactly that character. Okay, so let's now go back to cosmology. Here's an overview of quantum cosmology going from later to earlier. So from about 10 to the minus 12 seconds after the Big Bang through to the transparency epoch where we just discussed classically, we're in the regime of electroweak physics. We're in the regime of the Standard Model. I mean, a little bit of nuclear fusion, a bit of strong physics. Anyway, we're in Standard Model physics. This is well understood physics. It's strongly supported by terrestrial data. It is largely uncontroversial, relatively speaking. Prior to that, you get above the energy levels probed by the Large Hadron Collider, and indeed go back far enough and you get very dramatically above the energy levels probed by the Large Hadron Collider. In the mainstream challenged, speculative, but most commonly adopted approach to this epoch in contemporary physics, this gets called the inflationary epoch. It's a period where, go back far enough, then the universe is expanding exponentially, driven by a hypothesized new regime of physics called the inflaton field. This is a somewhat well understood extrapolation of current physics. There is some support from the data. That is, it's not simply hypothesized. It makes certain predictions for the form of the Planck satellite microwave background data. Those predictions are borne out, but they're scarcely precision tests. It's a sociological comment. It's widely accepted. It's certainly not universally accepted. And then you get to the Planck epoch, which is the breakdown of the whole quantum field theory model of doing physics, the breakdown of the idea of a background space-time on which physics plays out. This is what people usually mean when they say quantum gravity. I tend to say ultraviolet quantum gravity. The physics here is very speculative. It's also not under calculational control. So not only is it unclear whether the physics is true, it's unclear what the physics actually entails. There's virtually no observational evidence covering this epoch. There's no consensus about it. I want to talk about this period as basically as far back as you can go, while still saying we have some control over the physics at a level at which we can calculate and model. I'm not really going to defend the coherence of inflationary cosmology here. I'm broadly persuaded by the consensus that it's our best way to go at the moment. But in any case, if we're looking from the point of view of how quantum cosmology might sync with the Albert project, I think it's the natural thing to look at. So to do quantum cosmology in the inflation setup, we need to make a stipulation for what the initial quantum state is. Now, most of our use of quantum field theory, which is the quantum mechanics underlying this inflationary approach, is done on Minkowski spacetime, the flat spacetime of special relativity. Minkowski spacetime is time translation invariant. That means it has a coherent, conserved notion of energy. It's possible, therefore, to rank quantum states by their energies. It's possible to identify the lowest energy quantum state. By definition, we call that state the vacuum. And that state, by construction, is time invariant. And most of quantum field theory, generalizing in the particle physics context, explores various ways one excites localizedly interesting states out of that vacuum. You can't do that in expanding spacetime. And expanding spacetime is not time translation invariant. It lacks a coherent concept of energy. Therefore, it lacks the idea of classifying states in terms of energy. And the notion of a vacuum state, a lowest energy state, a ground state, which remains a ground state, is ill-defined. It is, however, possible to define a local vacuum state, what's called in the jargon of quantum field theory a Bunch-Davies state. And that state can roughly be characterized as a state that looks like the vacuum on short timescales. So, roughly speaking, the universe is expanding, but if you've got some process that is happening on a timescale very short compared to the timescale in which the universe is expanding, you can pretend it's not expanding. And you can say, what does physics look like at those short timescales, or what would it look like if the universe wasn't expanding, and then say, let's suppose it does look like that. That's a very hand-wavy description of something that can be characterized much more precisely in the QFT and curved spacetime literature. The assumption normally made in the inflationary literature is that that state is used as the initial state of the universe. If you posit that state and you advance it forward, then that state is homogeneous and isotropic, and the dynamics of the system is also homogeneous and isotropic, and the Schrödinger equation that governs quantum mechanics is deterministic. So the evolution of that state forward under the dynamics of quantum mechanics is into a homogeneous and isotropic state, unavoidably so. But just as we saw with the cat or the pollen grain, the state it evolves into is homogeneous and isotropic, but not macroscopically definite. It's a macroscopically highly indefinite superposition of a whole bunch of approximately classical matter distributions, each of which individually is not homogeneous at all, is not isotropic at all. And in inflationary cosmology, that process, that quantum mechanical evolution of a macroscopically definite, homogeneous state into a superposition of macroscopically definite inhomogeneous anisotropic states is the origin of the fluctuations in the early universe that seed structure formation. When I talked about inflation mechanisms of predictions, that's the form of the prediction it makes. That distribution I showed you on the night sky from the WMAP satellite, that's pure posit from the point of view of classical cosmology. In quantum cosmology, we're trying to derive it. And again, the derivation is scarcely a precision test, but one of the reasons inflation gets taken so seriously in contemporary cosmology is that it derives something that has the form given to us by the WMAP data. Now notice, the probability distribution I got over fluctuations there is completely quantum mechanical. I didn't say anything like pH mu. I didn't say, here is my probability distribution over microstates of the early universe. I said, the microstate of the early universe is this specific state. I haven't done my homework carefully enough to actually write it on the whiteboard, but it would fit. All of the probabilities that turn up there are quantum mechanical, therefore. And so the origin of all the probabilities we saw on that WMAP framework is quantum mechanical. And what those probabilities therefore are depends on how you think about the measurement problem. So go back to the Mentaculus again from that point of view. Remember, in the Mentaculus, we had the Newtonian law of motion, the past hypothesis, which was a hypothesis about the macrostate, and the statistical, a categorical hypothesis about the macrostate, and the statistical postulate, which is a probability distribution over microstates compatible with that macrostate. So here's what I think the quantum cosmology Mentaculus looks like. Again, remember, I'm talking here about the period of quantum cosmology subsequent to the Planck epoch. This is not a plausible candidate for the ultimate theory of everything, but it's the closest we've got at the moment. So the first statement of the quantum Mentaculus is analogous to the Newtonian law of motion, the quantum field theoretic laws of motion, which is that given by what I've called low energy quantum gravity in other work, the quantum field theory you get by just teaching general relativity as a field theory, plus the standard model of particle physics, the thing we've got out of CERN, plus the infiniton field, and there's a bump under the carpet for dark matter, and we don't know what that is, and there's a billion proposals of it, but the quantum theoretical laws would include the dark matter component as well. So that's piece one of the quantum Mentaculus. Then piece two is the past hypothesis, and the past hypothesis, the world first came into being in the local quantum state, local quantum vacuum state. And that's it. There's no statistical postulate at all. And notice there's in fact no postulate about macrostates at all. This is a sharply stated, microscopically precise statement about the initial state. Now, it's worth saying, incidentally, that the reason cosmologists use the local vacuum state is as much as anything about convenience. It's an easy state to write down. That's the state that Bunch-Davies messed with in early work. It's the state people run with. It's not that you couldn't, if you wanted to, suppose there's a bunch of other states, more broadly defined, that would also give rise to similar physics now. You could even put a probability distribution over them if you want to, and say that I'll select the initial state at random from that group. And maybe future physics will tell us that's the way to go. But nothing in current physics is requiring us to do it. Those probabilities over microstates were essential in a classical model, because firstly, because they're the tool by which we rule out anti-thermodynamic behavior, and secondly, because they're the underpinning, the ultimate source in a classical deterministic theory of the stochastic dynamic we notice at the macro level. But the underlying structure of quantum mechanics gives you those stochastic facts for free, so there's no requirement to go away from the this simple microscopically stated initial quantum state. Another way of putting it is, in classical cosmology, of course, the statement that the universe is asytropic and homogeneous at any given point in its evolution must be taken as an approximate statement, because look, the world is not anisotropic and inhomogeneous. But that argument doesn't apply in a quantum theory, because in a quantum theory, either emergently or fundamentally, quantum mechanical probabilities allow an initially exactly homogeneous, exactly isotropic universe to evolve so that the physics that we observe, whether that's all the physics or just the physics in our local branch, is a physics that has all these interesting, complicated structural features. So that's mostly what I've got to say. And I think you can see from this that the statements here is differing in some quite important details from Albert's framework. And yet I think ultimately in the same spirit as that framework, which again, I'm taking as given for this talk, but not defending. But I want to sort of stop by going back to finish by going back to that original setup that I quoted of Albert and the conversation we've got on the T-shirt and ask, what are we left with then? If we're sort of moved by Albert's slightly more metaphysical, slightly more, dare I say it, grandiose ideas about what we're trying to get out of the foundations of thermal physics, and we're looking for this best description of the world that best matches simplicity and strength. So the answer to that is now going to depend very sensitively on how you solve the measurement problem. If you solve the measurement problem the dynamical collapse way, which is to say you modify the equations of motion, then what you have on the T-shirt is the past hypothesis plus unitary quantum mechanics. You can, a ton of CERN postdocs will demonstrate to you you can fit the laws of quantum mechanics, of quantum field theory and the standard model onto the T-shirt. The font is quite small, it has to be said, but it does fit. And you've got the whole of the back of the T-shirt to add, to fill in the details about the inflaton field and to state the requirement that you've got the local quantum vacuum as the starting state. And you can even fit whatever supposed collapse law you add to the theory to solve the measurement problem. I mean, spoiler alert, there probably is no such collapse law, but assuming for the sake of argument that advocates of collapse theories can find one. Anyway, that's how it looks like there. But notice, of course, from the, if we're interested in this kind of simplicity and strength trade-off, then that stochastic collapse law is itself a certain compromise between simplicity and strength. It's to be understood as somehow a probabilistic description is the best we can do. If we have a hidden variable theory, something like de Broglie-Bohm's theory or a hypothesized relativistic version of de Broglie-Bohm's theory, then what the T-shirt has is the past hypothesis plus unitary dynamics plus the guidance equation that tells me how the hidden variables evolve, plus a probability distribution over those hidden variables, perhaps to be understood again in that kind of Humean compromise between simplicity and strength. God can't tell us everything. God can't tell us the precise micro details of where the hidden variables are, any more than God could tell us every way a dynamical collapse process happened over the history of the universe. But the best trade-off is to just write down this stochastic law in the first case, this probability distribution in the second case. And in the case of the Everett interpretation of many worlds theory, the T-shirt has the past hypothesis plus unitary quantum mechanics and nothing else. The God of the Everett interpretation is not interested in compromising. The description she's got on her T-shirt is not some best simplified description you can give of the universe within our available capacities. It's the complete description of the universe with no compromises at all. I'll finish there. Thank you.
Okay.